I will try to say true things, or at least mostly true. Anyway, Heavenly Father, we thank you for this day. Again, Lord, I thank you for all the students who could be bothered to come to this class today, and just pray that we would use this time wisely to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Sorry, I'm misbehaving slightly. So we are now into chapter 18 of Dummett and Foote, and this marker's weird. And so chapter 18, this is a really weird marker, is on representation theory and character theory. And so of course, the topic of representation theory is way, way bigger, I think, than this chapter. What gets called representation theory these days is very broad, but in particular, we'll be focused here on what's called group representations, all right? So let me just define for you, to get us started, what exactly is a group representation. And so here it is. Let G be a finite group, F a field, V a vector space over F. So G, finite group, F, field, and V, a vector space over F. All right. Then 1. A linear representation of G is what? Is any homomorphism I'm going to erase. I'm going to underline that there. Any homomorphism from G to GLV. The degree of the representation is the dimension of V. All right, so in other words, if you had a group and you had a homomorphic image of it in linear transformations on, a 5-dimensional vector space, then that would be a degree 5 representation, okay? 2, a matrix representation, so let n be a natural number. A matrix representation of G is any homomorphism from where? From G to GL and F. I'm going to start double barring my F because it just feels right, if you don't mind. And what's that? Feels right. It feels right, yeah. It feels, it feels good to do it, right? Let's see here, 3. That seems wrong. A linear matrix, well, a linear or matrix representation is faithful if it is injective. What's that? Very sweet. I don't understand you guys.
It's 1 to 1.
Oh no, I feel like I'm about to walk into some sort of dark world of puns where I may never return from. Let's see here. 4, the group ring of G over the field F is the set of formal sums things like sum over G in G of alpha G G for alpha sub G in the field. So basically we're looking at all F linear combinations of group elements with component-wise addition and multiplication defined in the natural way. And extend, well, let's see here. What do we mean by that? Let's see. So how should we add things in this group ring? Add matching coefficients, right? Yeah. So if I had sum over, say, alpha, sum over G and G of alpha G G plus the sum over G and G, beta G G, that would be the sum over G and G of alpha G plus beta G G, right? Scalar multiplication, how would you do that? I mean, this is actually, I should scalar multiplication, but I guess I mean, it's a group ring, right? So, yeah, what should I say here? Oh, just multiplication, yeah, thanks. How would you multiply them then? How would I multiply this times that? How would that work? All these engagements, it's distracting my classes. Let's see here. What's that? Distribution? Yeah. So I'm not sure how to write that in this notation. Right? Yeah, I'm not sure how I would. I'm not sure. I don't know. Like at this point, I'm like, I don't really want to write this down in this notation, right? So what did we say about G? It's a what? A finite group, right? So we could actually write G as the identity, and then like G1, rather, let's say G2, right? G3, Gn, right? There's n things in the group, right? And so typical thing in the group ring, right? What do we call that thing? Sorry. He didn't actually give me a symbol for it there, did he? We call it FG, though. So FG is things like sum I equals 1 to n, right, of Ci Gi, such that Ci is in the field, yeah. And here I'm just saying E is equal to G1 for the sake of my discussion here, yeah. Let's see here. So how would we, how's multiplication work then? You said you just distribute, right? But simple elements first. That's not a bad idea. So if I have something like a simple element would be like C times Gi, right? And then, C prime times Gj or something, right? Those are simple elements. They're product. What we do, we just C times C prime and then Gi times Gj, right? And then if you had sums of two things, how would you do it? You know. This is just an example, obviously, right? This would be what, C1C, G1G plus C2C, G2G, etc., right? I think one way we could look at this thing is, basically to define the group, we could define what are called structure constants for the group, right? Like after I pick G1 through Gn as a basis, as a label for the group elements, to define the group multiplication really is to do what? I think we could say what? Gi times Gj is equal to what? It's equal to a sum over k of, let's say, Cij k, right? Gk, right? And now what would these constants Cij, Ijk look like? The point is it's a group, right? So the product of any two group elements has to, again, be a group element. So that means that this Cij's either are what? They're ones or zeros. There's what? There's only one, and for example, if we had E times Gj, what would we get? We get Gj again, right? So this would tell me that, on the other hand, this, of course, is equal to the sum over, in my current notation, C1J k. K equals 1 to n, right? So if you look at that, you can actually see what the structure constants have to be in that case. What are they? Oh, thank you. Yeah, C1JK would apparently just be Kronecker delta JK, right? What's that? Jess, you are a bad influence.
I didn't do that. What did I do?
I have had Leah in other, well, I don't know if I've had you in other courses. Have I had you in other courses?
Abstract 1.
Abstract 1, right. But I'm thinking back to Abstract 1. Do I remember you saying any puns in Abstract 1?
Probably not.
No. There's a corrupting influence here.
There were more people then, so I was vocal.
Yeah.
I blame Jess. He is corrupting.
Whoever made the faithful comment?
Ever since the Tower of Babel comment.
That was good.
Yeah, that was great.
You didn't say that next time you said things.
That is true. I have told many of my friends that one. But all right. Anyway, so I make a long story short here. This group ring, right, is basically a vector space. It's a vector space over the field, which is the dimension. The dimension of the vector space is the order of the group, and every element in the group is basically being treated as linearly independent, and that's what we're looking at here.
If we do that operation like we did there, and we obviously substitute the Kronecker in place of that C, like Cijk, where it was C1jk, would it maybe better define it up there in terms of just Kronecker deltas?
No, I don't think so, because it's rather complicated the way group elements multiply in general.
Okay.
Right? Like, for example, we could look at G equal to E, A, B, and then AB. Right? And, so you recognize this as the what? Yeah, this is the Klein 4 group. So let's see here. So E, E, E. So all of these are order 2 elements, and of course A times B is AB, and this is BA, which is AB, right? And AB times A is B, and that's A, and it's commutative, so this is A and this is B. So if this is 1, 2, 3, 4, if I look at, for example, A times B, that would be that's G1 times G2 in my current notation, right? And that's equal to what? It's equal to,
What would be G2 times G3?
oh, I'm sorry, I can't do math. Let's see here, G2 times G3, yeah, as you said. And that would be that, which is G4, yeah. But my point is, yeah, you're right, it's a Kronecker delta, but which one? This apparently is, it's rather complicated in general, the patterns, yeah. Let's see here. So he says here, FG, the group ring, is a commutative ring if and only if G is an abelian group. Does that make sense? So the ring multiplication here, which I have kind of sort of defined for you, basically we're saying that you multiply the simple elements in this way and then extend by basically make the distributive property true, and that uniquely defines the multiplication. Given that, you can see that this ring multiplication is commutative only if what? If you can, the C's are always multiplied. The constant, the field coefficients always commute, right? But if the group is non-commutative, then you couldn't switch the order of that, which is what you need, right? This simple element's kind of telling. See this, I can say, well, that's C prime C, right? But in order to go back to GJ, GI, I need that it's commutative, right? Once I have that, then I can do, if that is true, then I can rearrange C prime GJ, right, times CGI, and that would be what I would need for this group ring to be commutative. But I need that the underlying group is abelian if I want the group ring to be commutative, okay? What else? He says, well, I already said this, but he says the group ring FG is a vector space over F with elements of G as a basis. All right, great. I don't know. I think I'm going to take a step away from Dummett and Foote here for a little bit and just talk to you about some things I know, if that's all right. This is fine. This is good. But what is an example of a representation of a group? Maybe we should actually look at one of those. Yeah. Or let's look at the group ring of something and study it. All right, so here's, this one's okay, but I think I want to look at a different example, if you guys don't mind. In fact, I think I even want to expand the discussion a little bit, and I want to go from looking at group representations. I actually want to look at algebra representations, I think. What would an algebra representation be? What would a representation of what would an algebra be? We talked about algebra before, right? It was something like A, right? Which is what? It has a copy of the field in its center, right? So there's some field elements in it that commute with everything, right? And what else did we say about the algebra? Is a ring, right? And so an example of this would be if you have a vector space, right? And if you have a multiplication on the vector space, then that would define an algebra. Supposing that multiplication satisfied the usual distributive properties, I think. So if you had an algebra, assuming we know what that means, all right, then a representation of an algebra would be a homomorphism from the algebra, and instead of GLV, we'd use little GLV. The difference between big GLV and little GLV is this. Big GLV is the set of invertible linear transformations on V. Little GLV is the set of just linear transformations on V. So little GLV is all endomorphisms. Big G assumes invertibility. All right, so these are the automorphisms of G, whereas these are just all linear transformations of G, endomorphisms. And then likewise down here, it would be, instead of GL and F, you'd have from A to just Fn by n. All right, that would be an algebra representation. That's actually more what I'm interested in lately. Okay. So actually the group ring is an algebra, right? I think it's an F algebra. Here, let's be more specific here. How about this example? Let's look at G equal to, I don't know, how about 1 and I need a good notation here. How about C? I don't like that notation. I'm sorry. How about 1 and J? Such that J squared is equal to 1. This is a group, right? This is a group of order 2, yes? What's its Cayley table? Right, 1, J squared is 1, right? So it's fairly obvious that this is isomorphic to like Z mod 2Z, right? Mapping 1 to 0 and J to 1. All right, so what's the real, if we look at RG, what is that? It's real linear combinations of the group elements, right? So that's like A times 1 plus B times J, such that A and B are real numbers. What is this? Well, I mean, if you allow me this notation, this is really just, we could write this A plus BJ if you'll allow me that slight difference in notation. That's the group ring of the finite group of order 2. Written multiplicatively, of course, written as a cyclic group, right? But you know what these are, Cooper. Yeah, these are the hyperbolic numbers. You better know. All right? These are hyperbolic numbers. These are an example of an algebra. They're an associative algebra, right? So what's an associative algebra? So algebra A, what should we know about this? A is a vector space. Let's say algebra over the field F, all right? Let me try to gather some comments here. A is a vector space over F. That much has to be true, in my thinking. Algebra is one of those terms that somebody probably has given a different, more general, abstract definition of in some corner, right? But where I'm from, algebra is a vector space, and it has a multiplication. And that multiplication basically is something like A cross A into A again, right? And typical notation might be something like X star Y, well, X comma Y maps to X star Y, right? Just to give a notation, sort of an abstract notation for a second, X star Y. And I usually think about algebras which are linear algebras, in a sense. Linear in the sense that this multiplication is a bilinear multiplication, right? In other words, you have additivity in both slots of this map, and you can pull real scalars out. I'm sorry, you can pull F scalars out, right? So, say bilinear over F, yeah? And then, now this is extra, but A is associative. Sometimes that's an extra condition, but A associative means what? It means that X star Y star Z is equal to X star Y star Z. So, if you're given an algebra, you can naturally start looking at representations of it, right? Like how can we look at a representation of the algebra? What would a representation of the algebra be? So this is called the regular representation of an associative algebra. Is given by the map. Well, let's say the rule x maps to L sub x. So here L sub x is a mapping from A to A again. All right, where L sub x of y is simply equal to x star y for all y in A. That gives me a rule. I'm taking each algebra element, x, and I'm assigning it an endomorphism, L sub x, a linear transformation on the algebra. Right. That is a representation in the sense that I'm looking, and I haven't proved you it's a representation yet, right? But we can. And I need to assume, though, that the algebra is associative. Let me show you why. All right, so let's work out that this is actually, my claim is that this is a representation. Claim the regular representation is a representation of A on GLA. So first of all, first things first, let's prove that Lx, left multiplication by x as it's called, right? Left multiplication by x, if we act on what? Say cy1 plus y2, what do we get? But remember, we're assuming an algebra has multiplication which is bilinear, right? So that means that we can pull the c out and we can break up the addition. Lo and behold, we've got c L sub x of y1 plus L sub x of y2, which shows you what? Thus, L sub x is an element of GLA. It's a linear map on A. We need more than this, though, right? What else do we need for it to be a representation? That's just the most basic thing, is it's the right kind of object, right? It also has to play nice with the algebra, right? It has to preserve the algebra's multiplication, right? Into where? Now here, you know, homomorphism of G into GLV. What does that mean? What does that mean? Homomorphism says it's going from a group to a group. What's the group multiplication in GLV? It doesn't matter, actually, if I'm talking about, I mean, the group multiplication in big GLV is function composition. The algebra multiplication in little GLV is function composition. Why is one a group and one an algebra? Well, this is a group, everything has an inverse. Little GLV, not a group, everything doesn't have an inverse, and yet it's still an algebra. It's a ring, right? The sum of linear transformations is a linear transformation. The scalar multiple of a linear transformation is a linear transformation. It's a vector space, and composition gives us a well-defined ring multiplication in that vector space. Okay, so we need the homomorphism property, right? So here we go. Let's look at L of x star y acting on z. What's that give us? X star y, right? Star z, according to the definition. Am I wrong? But we're assuming our algebra is associative, right? So what's this? Star z like that, right? And yeah, that's exactly Lx of y star z, which is what? Which is Lx of Ly of z, right? Which, by the way, is Lx Ly parentheses of z for all z in the algebra. So, thus, L of x star y is equal to Lx composed with Ly, if you like, or just skip the circle. We're big boys and girls. We don't need the composition symbol anymore, do we? So there we go. I can take off the training wheels at this point, yeah? So that proves for an associative algebra, the regular representation is indeed a representation. Do I need anything else? I think I have everything. Right. Now, here's a question. Is it faithful? Is it faithful? Well, it does depend on the algebra, right? So for argument's sake, example 1, suppose my algebra is pick any vector space you like. You pick it. It doesn't matter, actually. Don't pick it. Arbitrary 1, right? Let x and y in V have multiplication defined by x star y equal to. What do you think? This is completely arbitrary. This is for any vector space. What do I have to put here? 0, right? I mean, 0 is the only thing that could possibly be it, given my question, yeah? 0 is common to all vector spaces. And if you think about it, that multiplication will stupidly be bilinear and satisfy the necessary criteria to be a multiplication of an algebra, right? But that will also make the regular representation be what? This will force the regular representation to be the set of 0 maps over the vector space. Which is a subspace of GLV. I mean, it is a representation, right? But it's not faithful. I don't think, anyway. What was the definition of faithful? Injective. What kind of injectivity, though? Injectivity of what? Of the homomorphism. I might be in trouble. Linear if it's injective. Let's see here. What's that?
It seems kind of like dumb that they make you come up with faithful. Like, why can't they just call it injective in the first place?
Oh, because faithful, I mean, it has to do with the idea of, I mean, what is a homomorphism? What is a representation? It's what it sounds like. It's a representation, right? So to say it's a faithful representation is what it sounds like. It is actually faithful. It's a faithful image, right? It's not half the picture or, just a slanted picture of your object. It's the real deal, just written as a matrix or written as a set of linear transformations, That's the idea of the word. I guess you could go back and say, why didn't we always say that injective is faithful?
I mean, yeah, true. Like that. But I mean, it just seems like injective is like kind of universal.
Yeah.
Sorry.
No, you're fine. But I don't think this is injective, right? Because we're looking at the mapping. We have psi of x is equal to the 0 map on V, right? For all x, right? So the kernel of psi is V, which of course is not equal to 0, which is to say that psi is not, injective. So it's not faithful, right? How about this, though? What if your algebra has a unity? What if your algebra has something in it that behaves like the number 1? That's what's called a unital algebra, all right? So definition. If there exists 1 in A such that 1 times x is equal to x times 1 is equal to x for all x in A, right? Then A is unital. So here's a theorem for you. The regular representation of an associative unital algebra over F is faithful. Okay, so let's see if we can prove it. So let 1 be your unity in your associative algebra A, right? And our representation psi, psi of x is what? It's equal to L of x, right? So suppose that psi of x was equal to 0. Now this 0 is what? This is the 0 map, right? On your vector space A, which again is also an algebra, right? So what would that say? Okay, so Lx of y is equal to 0 for all y. Very good. What's that say? X times y, right, is equal to 0 for all y. I had a homework problem like this in linear last week. They're doing all this complicated stuff, but they had the statement for all vectors, right? And I had to convince them that they could take the case x, is this problem? They had x with y minus z equals to 0 for all x in the vector space, right? What they have to do is they have to think, wait a minute, if I put x equal to that, then all of a sudden I get information. Because it's inner product, when I put it equal to that, then magic happens, and then I get that y minus z has to be the 0 vector, and consequently y equals to z. So this is a homework problem they had recently. This is much the same. So you got it for all y. Which y should you pick? x. See, my analogy is very misleading. I'm sorry. What have I done? That's an example of some very bad teaching. So, this, yes, there can be only one. All right, so x.
It was very misleading.
Yeah, actually. I'm kind of proud of that. If I wanted to do it on purpose, like if I meant to do it on purpose, it would be brilliant. But it wasn't. It wasn't. It was just a fortunate accident. I feel like anytime students are, well, no, I should stop with my false student comments. But anyway, so x, so that means that's x, which x is, but if x is equal, so x is equal to 0, which says that the kernel of psi is 0, which says that psi is injective, which says that this is faithful. What that means, right, intuitively, is that the regular representation of a unidal associative algebra is, in some sense, a copy of the algebra. So you can study the regular representation of an algebra and really understand what the structure of the algebra is. That's the idea here. So let's calculate what does the regular representation of this algebra look like? Yeah.
What would be the point of having a representation that wasn't faithful? Like, how would that be useful?
Well, in physics, we have groups that act on wave functions, and it's just not the case that the wave functions are always a faithful representation of the group, and yet those non-faithful representations appear in the equations of physics. I mean, for example, in quantum mechanics, we study SU2 or SU3 a lot. These groups, special unitary groups of order, 2 by 2 or 3 by 3 matrices. And you'll talk about things like a 3 of SU2 or a 2. I forget the notation exactly, but I mean, they actually have different sized representations of the groups that they look at according to the physics that they're looking at. And the study of how to actually construct the group representations of these things is rather involved. Now, the big story of it's actually given to us in one of the theorems in Dummett and Foote. I think Maskey's theorem basically kind of gives you this picture of what they look like. It's a lot like Jordan form. You get these direct sums of blocks. The blocks are these irreducible representations of the groups and so forth. And I'll try to get to some of that next time. Unfortunately, I had a faculty senate meeting today, which has ruined thinking for me today. But I can tell you what I know, so let me continue to do that. So let's find the regular representation of these hyperbolic numbers. And, so it's useful to have a notation. So here's my typical notation. Actually, what's my typical notation, Daniel? I forgot. But so like if A is the algebra, then I usually use M sub A. This is the regular matrix representation of A. Actually, it's worse than that. I usually, if I have the algebra with the basis beta, I put a beta here because the basis is the regular representation, matrix representation, basis dependent. To keep things simple in here, we'll look at the algebra being equal to Rn, and that way we can drop the basis and just use the standard basis. So, take A equals to Rn, so, beta equal to E1 da En natural choice. That allows me to simplify our life a little bit. All right. So, theorem for a associative unidal. And let's just keep things simple. A equals to Rn as a point set. All right. Algebra. The regular matrix representation M sub A, which I'm going to define to be matrices of the following form. It's just matrix of L of X such that X is an A. My claim is that that forms a representation, where my L sub X is still left multiplication by X, right? Forms a matrix representation of A. Indeed faithful. A faithful one, because I'm assuming it's unital. So what again do I have to prove? I mean, I haven't actually stated the mapping, have I? So let's see. Let's say that this is, I need another letter. Give me a letter, any letter. 7.
Okay, I'm not sorry.
Q. Q. Okay, I'll use Q. Q goes from A to MA by Q of X is equal to the matrix of L of X, okay? That is the representation, the actual homomorphism, okay? So to show it's a representation, we need to show that's linear, right? Now, I would point out that Q of X is actually what? Q of X is what? It's equal to the matrix of psi of X, yeah? Where psi was the regular representation we just got into talking about. So it's actually the composition of two maps, right? It's the find a standard matrix for your linear transformation map, which I don't really have a good name for, but you've been tested on that, right? Like, here's the linear transformation, find its standard matrix. That is a mapping from linear transformations to matrices, which is, by the way, linear, because the matrix of a linear transformation plus another linear transformation is the sum of the matrices of the linear transformations, right? I mean, you know that if we have linear transformation T, linear transformation S, then the standard matrix of their sum is the sum of their standard matrices. You know this, right? And also, CT is C times matrix of T, right? So the outside function here is a linear transformation. And the inside function here is a linear transformation, because we already proved that. So we have the composite of linear transformations. Consequently, Q is linear. So that implies that Q is linear on A. And so the more interesting thing is the homomorphism property, right? So what happens if we have Q of xy, we get the matrix of psi of xy, right? I'm sorry, I should do x star y, right? The matrix of psi of x star y, but we just proved that that was what? Psi of x times psi of y, right? Would it be better if I did in the L notation? Let me do it in the L notation. I think it's more understandable in the L notation. Let me do the L notation. So this is L of x star y, right? But we just proved that that's L of x composed with L of y, right? And now, one of the crowning achievements of linear algebra is that the matrix of a composite of two linear transformations is the product of the matrix of the transformations, right? In fact, I try to tell you guys that that's why we define matrix multiplication, is precisely so that this happens. But that, of course, is what? That's Q of x times Q of y. So there you go. It's a representation. It's a homomorphism from your algebra to your matrix algebra, the algebra of matrices, right? Because the product, the sum of square matrices is once more a square matrix. Why is it faithful? Oh, what? Really? Oh, I'm sorry. It is faithful. Oh, man, I didn't get to the cool part. Curses. I'm sorry, guys. I will begin again Monday. So sorry. What's that? All right, fine. Well, Cooper has talked me into it. So what's, in our current notation, what's Q of A plus BJ? I mean, we need to figure out what's the matrix of L of A plus BJ, right? So what would this be? This would be what? This would be L of A plus BJ on E1, L of A plus BJ on E2, right? That's the standard matrix. But here we're looking at A equal to RG, right? Which we could also write as R direct sum JR. So basically, we're using the convention here. E1 is 1 and E2 is J. That's our notation. So this is exactly A plus BJ times 1. And this guy over here is A plus BJ times J. And so what you got is you got A plus BJ in the first column, and you've got AJ plus B in the second column. And of course, if you rewrite that in terms of E1, E2 type notation, right, that is exactly A, B, B, A. So there you go. That's the regular matrix representation of a hyperbolic number. We can set J squared equal to minus 1. And then this almost same thing will go through, except instead of having A, B, BA, we'll get A, B minus BA. But that wouldn't be a group ring, right? You see that? Like, the complex numbers are not a group ring, but the hyperbolic numbers are actually a group ring. Some algebras are group rings, some are not. Which ones are? I don't know. Some of them. Group rings are special. But anyway, I will try to do more of this sort of thing Monday and also try to say something meaningful from chapter 18. But thanks, guys. Sorry for going so far over.